Hello everybody. So last time we completed our discussion on the multi-view geometry, stereo systems, and at the end of the just a minute, I need to okay, I'm logged in now. Okay, so we talked about geometry of the multiple views. Also, we talked about how to establish correspondence. After the correspondence establishment, how we get the depth of the points, and under what conditions we can get them with the absolute coordinates, and under what conditions we get them with respect to a scale factor or with respect to a perspective projection transformation, etc. And at the end of the chapter, we said that dense methods, that is the correlation-based methods, are good. We like them. They produce disparity maps for the whole image, but they are kind of limited in terms of the images that we can use. They require textured images. They don't work very well for repetitive scenes, repetitive textured scenes. Also, they don't work for constant image areas, and they are sensitive to illumination variations, perspective changes. For that, we have the feature-based method. That means that we find the points of interest, okay, on the left and right image, and we match them, and we find their corresponding depth positions. Those are the feature methods. But feature methods are not good for dense estimation of the images. That's what we said, and they need a prior step of finding the points of interest in both the images, etc. So both of them have pluses and minuses, and both of them are used frequently for different purposes. That what we said last time, or maybe we didn't have time to talk about this, and we ended our discussion on the stereo like that. Okay. If there are any questions about stereo, I can talk about them. Otherwise, I will start a new topic.
I have a question about um, we are looking for some features that's matching. In stereo, we only look at the epipolar lines to search. But in other lessons, like in I think SIT lessons, we search whole image, and I think epipolar plane search is the difference of this. Am I understand it right?
Yeah, that's true. I mean, when you are doing the image stitching, when you are doing the homography estimation, at the beginning, if you have the epipolar constraint between these two images, that is, if you have the fundamental matrix defined on your pair of images, then of course you should use the epipolar constraint in searching the correspondences. But usually, you are just given two images without any epipolar constraints. Okay. Well, in that case, what are you gonna do? In that case, what you're gonna do is find the correspondences, without using the epipolar constraint, because you don't have the fundamental matrix. Remember, to get the fundamental matrix, you need a baseline. If you don't have the baseline is zero, stereo doesn't work. And usually for the image stitching, you prefer two images with a baseline of 0. because you don't want to introduce any parallax to your system. In that case, if you don't introduce any parallax to your system, then stereo is not possible because baseline is 0. In that case, f is not going to be found. And in that case, all you can use is the correspondences. You don't have the epipolar lines anymore. To be able to have the epipolar geometry, you need what? You need, where are my epipolar geometry? Epipolar geometry. Yeah, here it is. Okay, you need such a picture, but if you put O on top of O prime, there is no epipolar geometry anymore because there is no baseline. If there is no baseline, there are no epipoles E and E prime. If there are no E and E prime, there is no fundamental matrix. Okay, so if you have two images of the same scene, that doesn't mean that you could use a fundamental matrix, because fundamental matrix needs a baseline. And previously, what we did was previously we used the same camera and we rotate the same camera around the center of projection. Okay.
Thank you. And I have another question about we make our two-dimensional vectors on a polar line, as we say yes here OP, and we multiply it with a scalar, and then we find the line as a vector and a scalar. In this case, we know that two cameras OP and other OP would not intersect. So in this case, are we thinking that by multiplying it with a scalar, are we take two-dimensional OP thing to a three-dimensional thing, three-dimensional space?
Well,
by multiplying.
Well, I mean, with the epipolar geometry and the fundamental matrix, okay, all you are saying is that if I have a two-dimensional point, that is the image coordinates, let's say x1, y1, and 1, okay, I multiply it with this 9-element 3x3 matrix F, okay, and I think I put it in different, okay, this is x2, y2, and 1. This shouldn't be like that. This should be x1, y1, and 1, because that's the transpose, right? Okay, if I multiply this matrix with this one, I get a vector, okay, I get a vector, and that's the vector of the epipolar line. And if this point is on that line, then I should get a value of 0. That's all I am saying here. This one doesn't talk about what if these 2 points don't intersect because of the problems of the calibration and noise. And in real life, you will not get perfect 0 here, okay? You will get something close to 0 because of those intersection problems. And when you are doing the search, actually on that line, remember, for search, what did we use? We use sum of square distances or normalized cross correlation, right? So none of them are supposed to find the exact image window. SSD tries to be very close to 0, but it's not going to be 0 perfectly. Normal cross correlation, it tries to be perfectly 1.0, but it's not going to be 1.0 perfectly. So inside the fundamental matrix, you have this intersection problem built in already, and you don't expect to find a 0 here or 0 there or 1.0 there. So this is an optimization problem. You are trying your best to achieve the best match by considering what is in the image and by considering the values of the fundamental matrix. Did I answer your question?
Yes, okay, thank you.
Okay, good. Any other questions? Okay, if there are no questions, I am going to start geometric camera calibration. We talked about this a little bit, how we do the camera calibration. Remember, we have a projection matrix. Inside the projection matrix, we have K and R and T. Okay, intrinsic parameters, extrinsic parameters. This is a 12-element matrix, projection matrix M. If you multiply all these numbers together, you get a 12-element matrix M, projection matrix M. And whatever point you multiply with M, you get the image coordinates of the projected point. That's what we said before, in homogeneous coordinates, of course. Okay, so this is a 4-dimensional homogeneous coordinates of 3-dimensional point, and this is the 2-dimensional point in homogeneous coordinates. That's what we said. So with today's lecture, I am going to we are going to recover these values, the intrinsic parameters, the rotation matrix, and the translation vector of the camera itself. But while we are doing this, first we are trying to estimate what the value of M are, the 12 elements of M. That's the projection matrix. Previously we talked about it, but we are going to go into details of how we can obtain it. Later, from M, we are going to obtain these values. So the meaning of camera calibration is it is not recovery of the projection matrix M. Okay, recovery of the projection matrix M is a problem, yes, but it's not the same problem as the camera calibration. Camera calibration means that recover the values of K. That means, remember, what do we have in K? We have the focal length, we have the alpha value, that is the ratio of the width of the pixel to the height of the pixel. Also the theta value is the skew angle. Remember that, the skew angle theta. These are the parameters of our intrinsic parameters. Let's not forget about U0 and V0, principal points. If we get these 5 numbers, then we have the intrinsic parameters. For the intrinsic parameters, we have the rotation matrix. Remember, rotation matrix is an orthogonal one. R transpose times R is identity. That means that R transpose is equal to R minus 1. That's an orthogonal matrix, we know that. Okay, so recover a matrix such as R, which is orthogonal. Also recover this 3-dimensional matrix T, vector T. That's what we are going to do. So that's the geometric camera calibration. It is needed for many tasks in computer vision. For example, if you have a stereo system, right, and if you know the intrinsic and extrinsic parameters of both cameras, then you can get the fundamental matrix automatically, right, by multiplying K, R, T together, or essential matrix. Okay, so that's why we need camera calibration. If you have it, many things becomes much easier. Okay, many problems need the camera calibration, especially if you are doing a calculation like the distance from the camera, speeds of the objects, and etc. But many problems don't need the camera parameters at all. For those problems who need the camera calibration, this is how you do the camera calibration. The method that there are many camera calibration techniques. Okay, there are many camera calibration technique, and in fact, the most of the inventions about camera calibration is invented by the people who work on the maps. Okay, photogrammetry people, they try to make precise measurements using the camera images or the photographs. And when you take pictures of the mountains and the specific points of the scenery, you can make guesses about how far they are from each other or from the camera. And these information are very useful for producing maps of environments. Okay, so those people are very interested in camera calibration, and that's what we are going to see today. We are going to look at one of the classical methods of doing the camera calibration. Then at the end of the lecture, I will show you how to do the camera calibration using OpenCV procedures. OpenCV procedures is more practical, but the details of that method is a little bit more involved. That I don't want to go into the details of that method. Instead, I'm going to explain you how to get the camera parameters from a classical method. So this is our setup actually. Let's say I have an object like this. Okay, this object is the calibration object, three-dimensional object. I have this XY plane, XZ plane, and and this is XY, this is XZ, and this is the YZ plane. Okay, and they are perpendicular to each other, and this point here is my center of the world, 0, 0, 0. Okay, I know that one. And this point here is 0, 0, no. This point here is 1, 1, 0 in terms of millimeters. Okay, and here this is X. Okay, 1, Y is 0, Z is 1. Okay, you got the idea. So in terms of millimeters or centimeters, I have such an object. I place this object in front of my camera. Okay, and of course my camera's coordinate system is different. This is my camera coordinate system. This is the real world camera coordinate system, and I need to find the relationship between these two camera systems, rotation and translation, also the intrinsic parameters. That's the idea. So what am I going to do is, I know their real world points, right? This is 1, 1, 0, 1, 0, 1, etc. I know all the coordinates of all these points in terms of millimeters. If I take a picture of this object with this camera and I look at my image, on the image I know the coordinates, two-dimensional coordinates of all those points, right? So I know which point corresponds to which one. Okay, so for this pi, I have this small pi, right? I know the two-dimensional image coordinates of this pi, and I know the three-dimensional position of this capital Pi. And this my projection matrix gives me this relationship. So remember we talked about this, how we can find the parameters of the numbers inside this M, this 12 number M, this 12 element matrix M, 3 by 4 matrix M. we say that if I have enough number of correspondences, let's say I is from 0 to 11 point correspondences, should be enough for me to find or 12 point correspondences, should be enough for me to find the parameters of this M. Okay? So that's what we are going to do. Again, that doesn't mean that finding the values of M doesn't mean that we find the camera parameters, because camera parameters are these matrices, not these 12 numbers. But looking at these 12 numbers, we can go back and try to figure out these. Okay, good. So that's what we are saying. Assume that we have n image points, ui and vi, and we have the corresponding n word points. So I is from 1 to n. For each pi, I multiplied with m, I get the small vector ui vi. Well, of course it's a okay, k ui, k vi, and k in homogeneous coordinates. Okay, so that's what we know now. So let's use this relationship to come up with a large linear equation and solve that linear equation to get the values of m. That's what we are going to do. Find the values of m. Later, using m, try to estimate k, r, t. 3 by 3, 3 by 3, and this is a vector of 3 elements. Okay, so if I multiply all those values with the k and r and t values, this is the matrix M that I get. And I think I have shown you this before. And this is a 12 element matrix, 3 by 4 again. Let's look at this one. R1 is, do I have the R1? Oh, okay, do I have the R1 somewhere? Did I write it? No, I didn't write it. Okay, R1 is, let's say R is a 3 by 3 rotation matrix. Okay, this is what R is. It's a 3 by 3 rotation matrix. And R1 is this. R1 is this one. This one is R1. And this one is R2. And this third one is R3. So R1 is the first column vector of this rotation matrix. Okay, that's what R1 is. So this one says that multiply transpose of R1 with alpha, then minus alpha times cotangent theta R2 transpose, and U0 times R3. So alpha is the ratio of the height of the pixel to the width of it. That's the aspect ratio. Theta is the skew angle. U0 along with V0 are the principal point coordinates of my camera, intrinsic parameters. So can you tell me what kind of mathematical expression is this? What do you get from this expression? Do you get a scalar, or do you get a matrix, or do you get a vector? What?
It should be a vector.
It should be a vector. Why? Because alpha is a scalar. Scalar times a vector of rotation of a transpose of a vector, minus scalar times vector, plus scalar times vector. Okay, so if you add them 3 together, you end up with a vector. So this is a 3 element vector. This one is a 3 element vector. 1, 2, 3. Of course, the transpose of a vector. The same thing here, the same thing here. How about this side? This one says that alpha times tx. Tx is the T is a 3-element translation vector. Its elements are Tx, Ty, and Tz. So Tx, Ty, and Tz are 3 scalar values. Okay, 3 scalar values. So scalar times scalar minus, scalar times scalar times scalar plus, scalar times scalar. So it's a scalar value. So this one here is just a scalar. So that means that 1, 2, 3, and 1 here, there is a 4-element vector, transpose of a vector at the top row. I have three rows and 4 columns. Okay, 3 by 4 matrix, 3 by 4 matrix M. That's the projection matrix. So if I estimate this projection matrix, these 12 numbers, that means that I have only can recover this Tz value, maybe the third columns of the rotation matrix, and the rest of them I need to figure out. Tx, Ty, theta, alpha, and the elements of the other rotation vectors needs to be estimated. Okay, so that's what we're going to do after I estimate M. Let's try to estimate M first. Okay, I know this one, M times P, and if I divide the resulting value with Z, I get the two-dimensional non-homogeneous position of the corresponding point of my image. Okay, I know that one. So in this case, that's what I am going to do then. Well, M is a again, I am writing the same thing over and over again, but just to make it clear. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and P is a 1, 2, 3, 4, three-dimensional representation of point P in homogeneous coordinates. Okay, so I will call this row M1. Okay, this is here M1, and this is M2, and this is M3. So when I do that, when I multiply N1 with P, okay, that's going to give me a what? What does this give me? A vector or a scalar?
It will be a scalar.
It will be a scalar.
Sorry.
It will be a scalar, exactly. M1 times this vector, it's going to be a scalar. So then I will multiply M2 with P, and I will multiply M3 with P. So this one will give me, the corresponding points, okay, in homogeneous coordinates. So it's going to be small x, small y, and small z. To get the non-homogeneous coordinates in x and y, what do? I would say that x over z is my image coordinate u, and y over z would be my v. Okay, but what is x and what is z? My u is going to be in that case, m1 over p, m1 times p times over m3p, and my v is going to be m1p over, m2p over M3P. Okay, good. So I know that one, and this is what I get. U is here, M1P over M3P, and V is this. Okay. If somebody gives me corresponding points between the image coordinates and the real world coordinates like that one, I can write these equations. And if I do the linear algebra or just simple algebra work, this is what I would get, right? I would say, okay, this is U times M3 times, how do I take this one? U times M3 times P is equal to M1P. So if I try to isolate Pi like that, that's what I would get. I would say M1 minus U M3 times P is 0. That's what I would get. Of course, I don't have a single correspondence. I have many correspondences, so I will say Pi times this is going to give me a 0. So for a single correspondence, I get two equations.
Can I ask something?
Sure.
Why does it say in the slides that M1T and 2T, the transpose of them are equivalent to the rows, actually? Because the thing you did was, you just named M1 the row itself, so, but your equations seems to be more correct. I don't know.
You mean M1 minus UI M3 is...
No, in the...
You mean these are the same, so it is 0? Is that what you're saying?
No, so there's this sentence, if M1T and M2T and M3T denote 3 rows, under the formulas.
Are you talking about this slide or previous, like this slide?
This slide.
You mean this slide?
No, previous one.
This one?
Yes.
So you are saying that what if 2 rows becomes equal?
No, I'm talking about the first sentence of the second paragraph.
Okay, if M1T, M2T, M3 denote the 3 rows of M, yes. It follows directly from...
We denoted M1 as the row itself.
Yeah.
We didn't.
M1 is the first row, M2 is the second row. You are saying that this sentence doesn't make sense?
Yes.
Well, I mean, okay, these are the rows, right? M1 is the row. If you take the transpose of it, it becomes a vector. It's just a... this is not a vector, okay? These 4 numbers is not a vector. This is just a matrix of one column, one row, okay? Vectors are represented that way. So if you take a row like that, and if you take the transpose of it, it becomes a vector. And if M1 is a vector, and P is a vector, I can do the dot product of these two vectors. It's just a notation thing.
Okay, that's dot product.
So this is a dot product, yes. That's why it is dot.
Okay.
Oh, is that what you're saying? Okay. So this is not a dot product, this is a matrix multiplication, but this is a dot product. Yeah. If you like to do it with no dot product, then in that case you would say M1T and get rid of this one. So you would say M1T, M1TP. Okay,
Okay, thank you.
good. Okay, good point. Thank you. Okay, so I like this one. Why? Because every correspondence between the real world image coordinates and the real world coordinates and the image coordinates is going to give me these two equations. Okay, if I keep, okay, tell me, if somebody gives me the correspondence between the pi and the ui's, what are the unknowns in these two equations? What are the unknowns? How many unknowns do you see in these two equations? How many unknowns do you see in these two equations?
Two M1 and M3.
M1, M3, M2, M3, right? So I have M1, M2, and M3. Each one has 4 numbers in it, so there are a total of 12 unknowns. But I have two equations. So for each correspondence, I can get two equations, but 12 unknowns. That means that I need 6 correspondences, right? If I have 6 correspondences, and each one will produce me 2 equations, that should be enough for me to get all of these 12 unknowns. Okay, that's what I'm going to do. So I am going to find 12 correspondences between this 3D object and between my 2D images. And after that, if I am clever enough, I can write one big matrix and solve it. That's what I'm going to do. Okay, so this is what I know, and I like to write something like this. P is a large linear system. M is my vector of 12 unknowns. So M is going to be M1, M2, and M12. Okay, maybe I shouldn't, maybe let me do it this way. Okay, this is M11, M12, M13, and this one is M34. There are total of 12 numbers. Okay, so M is a 12 element vector. What is the size of P? Can you tell me the size of P? If I have 6-point correspondences, what would be the size of P?
It should be 12.
P is a matrix. P is a matrix.
2 by 6.
Well, I mean, in order to multiply this P with this matrix vector of 12 numbers, there are 12 numbers in here. So this one should have 12 columns, right? It should have 12 columns, otherwise I cannot multiply it. Okay, how many rows should I have? Well, it looks like since I have 12 unknowns, I should have at least 12 rows, but usually I will have much more than 12. I will have many more correspondences. So it's going to be larger than or equal to 12. So how do I get this P? This is what I'm going to do, okay? Remember, this is how I started. Each one is an equation, but I like to have an equation like this, a linear system. M's are the unknowns, 12 unknowns. P is the matrix of the numbers. They are all known. And each one, okay, it is not that difficult to actually figure that out from this equation. P1T, okay, transpose of P1. P is a vector, right? P1 is a vector of size 4. And if I transpose it, it becomes a 4-dimensional row vector. And this is 0, 0, 0, transpose of it. 4 numbers. And this is minus U1, P1T. So if you look at this one, I multiply this one with this, and I multiply this one with this. So I end up with this equation. You understand, right? P1 times M1, like this, minus U1 P1 M3, this. And then I do the same thing for the second row. So what these two are saying is expressed in these two lines. In two lines express this one for a single correspondence. And I have n correspondences. So this matrix is going to be n by 12. This is a n by 12 matrix. Okay, I have a linear system. I know the values of P. I don't know the values of M. If I multiply P with M, I should get a value of 0. And solve this. Okay, tell me a solution for this system. Just look at this equation. Okay, P's are known, M's are not known, right? Tell me a solution. Just now. It's ready to see a solution now.
0.
Yeah, if I assign all values of 0, 0, 0, 0, 0, it's a solution, right? That's good. That's a solution, but we don't like this solution. This is a trivial solution. With the trivial solution, it doesn't matter what kind of P I have, what kind of correspondence I have. M being 0 is a solution. Okay, it's mathematically valid solution, but in practice, this doesn't work for me. So we don't like the trivial solutions for this purpose. We need non-trivial solutions. Okay, I am going to get a non-trivial solution. I'm going to get a non-trivial solution. I need to find it. But again, whatever we faced this problem before many times. Whatever solution you found, okay, let's say you found this set of M values, 12 numbers. If I multiply that M with K, a constant K, a scalar K, that's going to be a solution too. Because we know that if P M is 0, then P times K times M is going to be 0 too. So this Km is going to be another solution. So there are infinitely many solutions to this system. And each one is related by a scalar like K. Okay? By a scalar K. So they are all dependent on each other by a scale factor. That's what we say. By a scale factor. So don't get too excited when you solve this equation. You will get an M, but your values of M, even though they are defined as your projection matrix. Let's go to this projection matrix again. When you find those 12 values of M, that doesn't mean that you found TZ, or that doesn't mean that you found the third column of rotation matrix R. Okay, because whatever I found, if I multiply it with something K, is my solution again. So I found TZ, or I found R3 with a scale factor Ka. And I don't know what that K is. And I am responsible for finding that K value. I should do that too. Okay? So keep this in mind. Okay, any questions up to now? So how are we going to solve this one? How are you going to solve this one? How would you solve P times M is 0? From your linear algebra classes, remember it. How would you solve this one? Gaussian elimination. The methods that you have learned, the trivial methods that you have learned. Well, what happened? What happened? My my draw board crashed. The methods that you have learned in the simple methods that you have learned for solving the equations like this will give you the trivial solution for you, and we don't like the trivial solution. Okay, I am at the same one. Okay, we need something different. Maybe we can do this. Okay, it's okay. Tell me how I would solve this using the methods such as Gaussian elimination. You cannot directly apply it. Tell me how would.
I remember parametric solution. I think we turned them to a vector and multiply them all columns with a scalar. Parameter. Like
Yeah, after you solved it, yes, but I am talking about finding the values of m other than 0. How would you find it? One method is this. Since whatever I find, I can multiply it with a k, I am going to assume that the the last element of this m is 1, and all the others m11, m12, m13 up to m33 are unknown. So I'm going to assume that 11 of them are not known, only one of them is known. So since this is 1, the others cannot be 0 anymore. Okay, so I force the problem to become a problem that the trivial solution is not a solution anymore, because since I accepted this as 1. Can I do that? Yes, I can, because as I said before, whatever solution I can find, I multiply it with a k, and it becomes my solution. After I found my solution, I can multiply these all 12 values with k. Now k1 becomes k, and all the others change accordingly. So that one solution could be this. But there are some numerical problems with this solution. Okay, although this is a good idea, we like to do it in a better way, more mathematically sound way. Linear algebra defines very nice ways of solving these kind of systems. By the way, these are called homogeneous systems. If you have a matrix like this, and if you multiply it with or maybe A is a matrix, X is a vector unknown. If this one is a 0, this is called a homogeneous system, homogeneous linear system. Homogeneous linear system. And there are very mathematically and numerically sound ways of solving these kind of systems, and I'm going to look at that one. Maybe you will remember it. The answer is singular value decomposition. Okay, we are going to do the singular value decomposition, and it has many advantages, and we are going to use singular value decomposition to solve such systems. But it looks like I'm out of time for the first part of the lecture. Let me take 10 minutes of break. Let's be here around 14:34, and we will continue afterwards. Arkadayım ya, sonra ya. Şimdi başlamam lazım. So the singular value decomposition is a way of doing many useful stuff in linear algebra. But we are going to mainly use this technique for solving homogeneous equations. In this case, since we are already talking about it, I'd like to spend maybe 10 minutes to talk about this single value decomposition where we can use it anywhere else. Any matrix A, any matrix doesn't have to be rectangle, doesn't have to be square matrix. It could be rectangular. Any matrix can be decomposed into these three matrices: U, D, and V. D is a diagonal vector like that. Okay. Diagonal means that only the diagonal elements are non-zero. Only the diagonal elements are non-zero. Other than the diagonal elements, they are all zero. Okay. And we have this U matrix, and we have this V matrix. We remember we note that we represent V as VT because the columns of V and columns of U are important for us. Okay, but the decomposition works this way: U times D times V transpose. Okay, D is a diagonal matrix, as I said before. By the definition of the singular value decomposition, the value of sigma 1 is greater than or equal to sigma 2, greater than or equal to sigma 3, and they are all greater than or equal to sigma n. And they are all greater than or equal to 0. So that means that it is possible that all the sigma values could be 0. Okay, because if they are all equal and they are all 0, it could be, that's possible, but that's a very rare case. And if any of the sigma values is going to be 0, then it has to be start from the sigma n, because sigma n has to be the smallest one. Okay, so these sigma values are the singular values of this matrix A, and they are all fully determined by A. Okay, those are the singular values of matrix A. What do we mean by singular values of A? We are going to talk about it in a few minutes. Okay, both U and V again are determined by A, but they are not unique. Okay, different type of singular value decomposition algorithms could produce different U's and V's, and different algorithm steps are going to produce different U and V's. But whatever you do, always the columns of U and V are orthogonal. That means that if I do a dot product of this column with this column, it's going to produce a 0 because they are orthogonal. They are perpendicular to each other. And this one is perpendicular to this one and that one, etc. Okay? So they are perpendicular to each other. They are orthogonal, mutually orthogonal. Good. Okay. So these are just properties. So far, I didn't say anything useful yet. Let's look at the useful stuff about the singular value decomposition where we can use it. Okay. This singularity condition. Look at this number. Sigma 1 over sigma n. Okay, maybe before that one, let's look at these singular values. We say that A is non-singular if all singular values are non-zero. If all of them are non-zero, they are nice numbers, they're larger than 0, we say that A is not singular, is non-singular. What is a non-singular matrix? Can anybody tell me? What is a non-singular matrix?
a matrix whose inverse is not existent.
Yeah, okay. A non-singular matrix, singular matrix is a matrix that cannot be inverted. Okay. If I don't have an A minus 1 of a matrix, this is a singular matrix. A non-singular matrix is a matrix that we can take the inverse of. And once you have the inverse of a matrix, for example, if you have this AX equals B, okay, if I can take the inverse of a matrix, then I would do this: A minus 1 A equals to A minus 1 B. So these cancel each other, so I solved it, right? So there is a solution to this linear system if I have a non-singular matrix. So they say that if all of these values are non-zero, then I can find the inverse of this matrix nicely. But how about this one in this computer? Okay, this is in theoretical world. Whatever I said, if they are all non-zero, then I can find inverse. In the computer world, I run this decomposition. However, I did it. Okay, I ran this decomposition, and I found sigma n to be 1 times 10 to the minus 30, 10 to the power minus 30. So this is non-zero, but this is very close to zero. Do you think this matrix is a singular matrix or non-singular matrix? Can I find the inverse of it?
We can, but it will be prone to error because it's a very small number.
Yeah, it is prone to error. Why? Because this number is so small. I mean, probably it's a precision error that maybe I should get a 0, but I'm not getting a 0 because getting a 0 is really difficult if you are dealing with the double points, right? Double numbers or floating point numbers. That's going to be difficult. So there is going to be a numerical degeneracy case in this one. Numerically degenerate case. Why is it numerically degenerate? Because this one is very close to my precision, numerical precision. Okay, so theoretical world is a little bit different from the practical numerical analysis world. So I should be very careful here. So how should I be careful? This is what they say with the singular value decomposition. Just divide this sigma 1 with sigma n. I know that sigma 1 has to be larger or equal than sigma n. If this number is very, very large, or just the opposite of it, sigma n over sigma 1 is comparable to be my arithmetic precision. Okay, with the doubles I can soundly represent numbers with like 10 to the power minus 20, yeah, but 10 to the ten to the power minus 300 is not a good thing. If you are getting values like that, then you are in the dangerous waters. Okay, you are running very close to your limits of arithmetic precision of your CPU, of your processor, and that number is very important. So always check this number. That's called the condition number. Check the condition number of your matrix after the singular value decomposition. If the condition number is very close to your arithmetic precision of your machine, then you may consider that matrix to be singular. Okay, don't try to solve that equation because there is something missing. Okay, good. So that's the first important thing. So that's the first important thing in terms of numerical analysis. Okay, the worlds of computers and the world of theoretical mathematics are a little bit different. With the world of computers, okay, we have to be always careful with the arithmetic precision of our algorithms. Okay, so you cannot assume arbitrarily precise machines. We have limited capabilities. Our capabilities are nice, but we have limited capabilities. I cannot represent all kinds of large and small numbers. There is a limit. There is underflow and overflow problems. Okay, that's one thing. The second thing is the rank of a matrix. Remember, we used to calculate the rank of matrices. It is easy to calculate the rank of matrices. The rank of matrix A is the number of non-zero singular values. So you just count the number of non-zeros. You will say this is non-zero, non-zero, non-zero, non-zero, etc. Okay, I have 7 non-zero numbers in this diagonal, and my rank is 7 in that case. Of course, with the numerical methods, when you do the singular value decomposition, you will rarely get zeros for these diagonals, for all of them. Okay, some of them will be very close to 0. In that case, I should use some kind of a threshold. If a number is non-zero, if it is larger than some value, so there should be a threshold. That's the rank of a square matrix A, is the number of non-zero values. Okay, another nice thing is this. Okay, taking an inverse of a matrix is difficult, right? You need to do lots of stuff. Taking an inverse of a matrix is difficult, but once you find the inverse of the matrix, you could do this. You could get the solutions of such linear systems. You could get the solutions of such linear systems. That's fine. But how am I going to find the inverse of a matrix? This is what you do. If A is non-singular, inverse of a matrix is this: V times t to the minus 1 and ut. It is not, remember, this is the singular value decomposition, u d vt. Now v times t to the minus 1 ut. So do the singular value decomposition, replace u and v like that, and take the inverse of d. But you might say that, how am I going to take the inverse of d? It is difficult, but it is not. Taking the inverse of d is very easy. Why? Taking the inverse of this the diagonal matrix is very easy. What is the inverse of this one?
I think it's not orthogonal, but I think
It's going to be d to the minus 1 is going to be, it's all zeros everywhere. It is all zeros everywhere, right? Other than the diagonal, and in the diagonal it's going to be 1 over sigma 1, 1 over sigma 2, etc., and 1 over sigma n. So that's the inverse of d. So it is very easy. If you have a diagonal matrix, taking the inverse of it is taking the 1 over values of those diagonals, and that will be your inverse of it. That's why if you have this decomposition done, why do I say that? Okay, why do I say that if A is non-singular? Why am I saying this? Why do I have this condition? I mean, if I remove this, inverse of a matrix is this. If I say this, what would be the wrong thing?
Then singular values will be 0. And,
Yeah.
1 over singular values.
1 over 0 is going to be a problem, right? Yeah. Well, what is a singular matrix? Some of the elements of this diagonal are 0. I cannot take 1 over zeros, right? So it has to be non-singular, okay? If A is non-singular, then I can take the inverse of all the diagonal elements, and that's going to be give me the if some of them are 0, then in that case I am not out of luck. I would use this in general. The pseudo inverse of A is this, and in that case I wouldn't show it as A to the minus 1, but I would say A plus. A plus is the pseudo inverse of A. So how does it work? If this is my D, let's say 7, 5, and 0, so this is a singular matrix, right? This is a singular. I cannot take D minus 1, but in this case, this is what I'm going to do. this is d0 minus 1 is equal to 1 over 7, 1 over 5, and don't change this one, take the rest as 0. Okay, this is d0 minus 1, and multiply this with, okay, multiply with this v d0 minus 1 ut. Okay, that's how we get it. So a plus shadow inverse of a can be obtained this way, and with the shadow inverse of a I can get some kind of a solution to my linear system. And remember, okay, this is the third useful thing. And remember our eigenvalues and eigenvectors. Using single value decomposition, you can get the eigenvalues and eigenvectors. Okay, this is the rule. Okay. By the way, these are all the rules, and they can be proven that. Okay, you can prove that these are all valid rules. Since we are not doing a linear algebra course here, I'm not going to prove anything. I'm just giving you the rules, like drug capsules, and you are supposed to swallow them. And if you like to see the proof of these, go back to your linear algebra. Did they prove anything about the singular value decomposition when you take the linear algebra? Did they prove it, or did they just tell you about the rules? Tekil değerler ayrışması, I think that's the Turkish name for it. Singular value decomposition. I don't think that they prove anything. They just tell you the decomposition, and that's it. Okay, that's fine, no problem. We are talking about it. Eigenvalues are eigenvectors. Okay, if I have a matrix like A transpose A transpose times A, or A times A transpose, okay, their eigenvalues are sigma squares for all the sigmas greater than 0. Okay, that's the rule. So those are the eigenvalues. So eigenvalues and the singular values are related. Eigenvalues are the sigma squares of ATA and AAT. And columns of U are the eigenvectors of ATA, AAT, and columns of V are the eigenvectors of ATA. By the way, since A is a M by N matrix, okay, AAT is an M by M matrix, and ATA is an N by N matrix. Okay, and by the definition of the eigenvectors, if sigma squares are eigenvalues, and if the vectors of columns of U are my eigen vectors, then AAT UI is sigma square UI, and this is valid too. So if you are going to do the eigenvector analysis, then single value decomposition is something. But note that we are not talking about the eigenvalues and eigenvectors of A. We are talking about the eigenvalues and eigenvectors of AAT or ATA. Okay, good, and this is going to be useful for us too. And remember the least squares problems that we solved a lot. Okay, with the least square problem, I can put my problem into this position. AX is equal to B. With the least square solutions, usually the number of rows are much greater than number of columns. Okay, number of columns is the number of unknowns. Usually I expect that the number of columns and number of rows are the same for regular linear systems, but for the least square solutions, number of rows, that is the givens, are much larger than the number of columns. Okay, so how do we solve such systems? We take the zero inverse of it, because A is not a rectangular matrix. Okay, so this is what I do. I multiply both sides by AT. So ATA and AT, both sides are multiplied. So this is a rectangle. This is a square matrix now, n by n matrix. Okay, this is a vector again. What is the size of this vector? What is the size of this vector? Can anybody tell me?
And size.
Of course it is. Of course it has to be n. Why? Because this is n by n. If I multiply this n by n with this x, and x is an n vector, then it has to be n, right? Okay. So I multiply both of them. This is a matrix. This is a vector, and I take the pseudo inverse of it. Okay. Do the decomposition. Do the decomposition, singular value decomposition of it, and take the pseudo inverse of it. So the compute the pseudo inverse of ATA by singular value decomposition. Okay, that one doesn't have to be a singular matrix. Okay, it could be a non-singular matrix or singular matrix. Most probably it's going to be its rank is going to be less than n, but instead of saying that we cannot solve it, this is going to be there's an equal here. This is going to be a good estimate of the solution in terms of least squares algorithm. Okay, so single value decomposition to have with least squares works this way. We take the pseudo inverse and multiply it that way. So there is a theory of it, and there is an optimality for it. It is the same as doing least squares estimation using a linear system. And always try to keep an eye on the condition number. Condition numbers are important. Okay, now the main point that we are working at. If I have a system like that, note that this is different than this one. This is an homogeneous system. What do we mean by homogeneous system? Any solution that I can find for x is just a single solution. There are infinitely many solutions. Okay, my solution is scale dependent. If I multiply my solution with k, that becomes another solution. But this is not the case, right? If I find a solution for this x, multiply x by k, I have to multiply my b with k too, so that doesn't work. Okay, so homogeneous systems are different than this one. There is a trivial solution for this one, but there is no trivial solution for this system. Okay, so let's see how the homogeneous systems are solved with the singular value decomposition techniques. I have m equations and n unknowns, like in our case. Okay, and with this system, if I look at the rank of A, that is the number of non-zero singular values, it has to be n minus 1. If the rank of this A is full, if the rank is n, this cannot be a homogeneous system. The rank of A has to be n minus 1. I have to make sure that, okay? So there is a non-singular, non-trivial solution up to an arbitrary scale by SVD. And the solution is very simple. The rules say that our solution is simply, this word is important. It is simply proportional to the eigenvector corresponding to the only zero eigenvalue of ATA. Okay, let's look at this one. Let's look at this rule. Okay. We say that we take the singular value of a matrix A and eigenvalues and eigenvectors can be obtained. Eigenvalues and eigenvectors of ATA and AATA can be obtained using the single value decomposition. Okay. Take the smallest eigenvalue, which is the smallest singular value, and square, and the corresponding eigenvector is the last element of this matrix V. So the last column of matrix V is our solution. That's it. Okay. ATA, okay, ATA, the Eigen Analysis of Ata is this. Sigma squares are the eigenvalues of Ata, and the columns of V are the eigenvectors of Ata. Okay, and in this case, if I have a system like that, take the singular value decomposition of A, and the last column of matrix V is our solution. So this simply says that don't do anything other than taking the single value decomposition of this system. That's it. That's what we are going to do. And taking the single value decomposition, maybe if you took the linear algebra class, or if you took the numerical analysis class, maybe you know how to do it. But if you don't know how to do it, don't worry. OpenCV provides plenty of functions to do those kind of stuff. There is a single value decomposition compute function. You take the input array, that is your source decomposition matrix, and it outputs 1, 2, 3 matrices for you. Okay. W is the singular values, U is the calculated left singular vectors, V is the calculated right singular vectors, and VT is the transpose matrix of the right singular value. So V and VT are the transpose of each other, same matrix basically transposed. And flags are the flags that you use for the single value decomposition. Basically, flags are telling you which algorithm to use for the single value decomposition. Let me go to the OpenCV SVD function. I cannot write function. Okay, good. Documentation. I'm trying to see what kind of parameters do I. Flags, modify A, no UV, full UV. Okay, these are the flags. What are the meaning of it? Can I modify A? I think you can OR them. Allow the algorithm to modify the decomposed matrix, can save space and speed. Only a vector of singular values is processed. To be processed. Okay, so just give me the singular values only. I don't need the U and VT. When you say full UV, I need everything. What is perform back substitution with the SU? Oh, okay. I will give you, do you understand this one? I will give you W, U, and VT, and you are going to produce the other side of it. Right hand side destination constant. Oh, okay, here it is. X is this one times this one times this one, and it is remember that one, solving the linear equation of least square sense. If I do this, it is equal to a minus 1 times right hand side, so it's going to solve it. Back substitution. Good. And this for the computation. Good. So there are many useful stuff here. So you check this page out and you're going to find useful information. Good. Okay, so to solve this problem, all I need to do is do the decomposition of A and take the last column of V, and that will be your solution. Of course, keep an eye on the condition number. Keep an eye on the condition number. Okay, that's what we are going to do. Okay. By the way, we could use singular value decomposition, many other things. Okay, singular value decomposition of many other things. For example, if remember our rotational matrix. Rotation matrix is a orthogonal matrix, right? That means that R minus 1 is equal to RT. That's what I know, right? Singular value decomposition says that if you have a orthogonal matrix, and if I do a singular value decomposition of orthogonal matrix, then your D value should come back as 1, 1, 1, 0, 0, 0, 0, 0, 0, like that. Okay, this would be your diagonal matrix. So orthogonal matrices have their singular values as 1, 1, 1. Okay, that's one property of the singular value decomposition. So if I have estimated the rotation matrix, and if I do the singular value decomposition, I would expect that there should be ones here. If they are not ones, then I can put ones in there and put them together back projected and get a new A value. So this one is guaranteed to have diagonal of ones. Okay. So I am enforcing constraint by SVD. I am enforcing the constraint that R should be orthogonal. R should be orthogonal. If I have a matrix A, I know that the rank of A is 7. So how should I make sure that it has a rank of 7? I would do the singular value decomposition. Okay, I would make all the elements after the 7th singular value elements to 0 and put them back together, back projected, and that way I would make sure that the rank of this matrix is now 7. So singular value decomposition is used for those kind of purposes too. That's why OpenCV had lots of back projection functions. This kind of stuff is used for enforcement. Okay, back to our original problem. Okay, back to our original problem. Remember what we did? Do I have it in here? Remember what we did? We did was, okay, I had a P matrix times M is equal to 0 homogeneous system. So this P matrix has 2n rows times 12 columns. N is the number of correspondences. For each correspondence, I have two equations, and there are 12 unknowns. Okay, so if I take the singular value decomposition of this P, after taking the singular value decomposition, take the last column of the matrix V. That would be my solution. Okay, that would be my solution for these 12 numbers. Okay. So my solution is going to be those 12 numbers. So M is equal to, what is M? M is a 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 3 by 4 matrix, and it is equal to K times R times T. But as I said before, this M is not unique because I can multiply that M with any number, any constant, that becomes another M. Okay, I have infinitely many M's that are related to each other with a scalar, but I have only a unique set of KRT. How am I going to find that scale factor between that M and KRT? So somebody said that, okay, let's express this as rho times A. There is a matrix A, 3 by 3 matrix A, and this one there is a column B. So A is a 3 by 3 matrix, B is a 3 element vector. Put them together. I don't know the values of A and B, but I know rho is a scalar times AB. Okay, and I know that this one is equal to my M vector. Okay, my M matrix. Okay, let's take this 3 by 3 part. Okay, let's take this 3 by 3 part and let's ignore this B for a while. Remember what was our M? Let's go to our M. Our M is, okay, this. Let me get rid of these, whatever I wrote before. So this is the part that is 3 by 3. Okay. I estimated this part up to a scale factor. So I know rho times A. Rho times A, I know this one. Okay. It is in my hands. I solved it. But I don't know A. I need to find the A. So how am I going to find it? I'm going to show you in a few minutes. I didn't use this part yet. This is a 3 element vector. Okay. It looks like, okay, the third row of A times rho is equal to R3T. Okay. What can you tell me about this one? What is R3 dot product R3? Can you tell me anything? How about this one? No. Let me show you. Let me ask you this. What is R1 dot product R2? R1, R2, R3 are the 3 rows of 3 columns or rows of the rotation matrix. So what is R1 times R2?
0 maybe.
It is 0, exactly. Why? Because,
So
yeah, RT times R is equal to 1, 1, 1, 0, 0, 0, 0, 0, 0, right? If I multiply the first column with the second column, I should get a 0 because I am getting 0 here. So they are orthogonal to each other. They are perpendicular. And similarly, if I multiply R3 with R3, I should get a 1, right? Because it says 1 here. Right? That's what I'm saying. So here, I don't know what R3 values are, but I know rho times R3 values. Okay? If I multiply rho times R3 with rho times R3 again, what would I get? I would get rho times 1, right? That's what I would get, rho times 1. Or sorry, rho squared times 1. So I know this one then. Then the numbers that I get from the singular value decomposition, the third row of this matrix A, if I dot product with itself, I am going to get rho squared, the number rho squared. If I take the square root of rho squared, what would I get? What is the square root of rho squared? Can anybody tell me? What is the square root of rho squared? What is the square root of rho squared?
The volume of rho.
Exactly, it is the absolute value of rho. for some reason today I cannot write row. It's like that. Okay, so absolute value of row. Okay, it could be negative or positive, I don't know. What is the absolute value of row? So by doing this, I estimated the value of row up to a scale factor. So it is, I know, plus or minus. I know the value, whatever I get, it is either plus or minus row. So by looking at this row only, okay, these numbers only, I estimated the row value, the scale value that is keeping my mind busy. But where am I going to get the scale value? Because I only estimated this up to a scale, etc. Right? So I found it. I don't know exactly what R3 is, but I know R3 up to a scale value now. Why? Because if I get the third row of this matrix A, okay, whatever I found, divided by this absolute value of row, I will get the R3. But I don't know if those numbers should be inverted or not inverted. Should I take the positive, negative, or not negative? Okay, good. Okay, but the nice thing is, doesn't matter what the R3 values are, doesn't matter the sign of it. If I multiply R3 with R3 again, so negative and positive doesn't matter, I should get 1, always 1. Okay, doesn't matter. And again, R1 times R2 has to be always 0. Doesn't matter what the sign of this R1 and R2 is. So let's go back again to the place where I said this. Okay, so we talk about this RT times R is identity. There is okay, this is kind of review what we mean by the rotation matrix. Okay, if there is a rotation of theta between this red coordinate system and the green coordinate system, then this would be the 3 by 3 matrix between these two. Right? We know this. And by looking at this is what I mean. Okay. These are the values that I have recovered by solving this P M equal to 0. I get the last vector of decomposition of P, single variable decomposition of P. That's my solution. But that solution doesn't give me the exact M. It is up to a scale factor. And those 12 numbers, I took the first 3 by 3. Okay. And I took the absolute value of A3. And I say that I took the absolute value of A3. And I am saying that my rho is equal to epsilon over length of A3. What is epsilon? Epsilon is either plus 1 or minus 1. So up to a scale factor. So I found epsilon up to a scale factor. There are 2 possible epsilons. So I kind of solved this epsilon, not yet. Okay, and by looking at this one, our R3 is rho times A3. Okay, remember M, I found M. It's 12 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the A part and this is the B part. This is A and this is B part. Okay. This last this row here. Okay, this row here is this one, but up to a scale factor like that. Okay, rho times A3 is R3. Rho, I know this is the value of rho, but rho could be negative rho or positive rho. Okay, good. So I almost found R3 up to a sign. Okay, let's go back to this matrix now. Again. Let's try to understand this one. If I take A1, raise this one. If I take A1 here, this is A1, and multiply it with A3. Okay, A1 is equal to this row, but multiplied with row. A3 is this row, and it is equal to this row, but multiplied with row again. Let's ignore the rows. Let's multiply this R3 with this one. Can you tell me what you get? R3 times R1 alpha. What does it make?
I think these are perpendicular vectors, so it has to be 0.
Yeah, so this one will cancel out. R3 times R2, again this one will cancel out. R3 times R3 is 1, right? And so this one will make 1, and I will get U0 only. So if I multiply this third row with the first row, I will get U0. But remember, I have the rows in it. So if I multiply A1 with A3, I will get U0, but now I have to factor out this row. There is a row square. Okay, so all I do is, out of these 12 numbers, multiply this row with this row. I will get U0 over row square. And if I multiply this part with the row square, then I will get U0. Okay, so do I have the minus plus part for the U0? Remember, I know row up to a sign. I know R3 up to a sign. Do I have the same problem with U0? Do I know the U0 exactly, or do I know U0 up to a sign?
We only have row up to a square, so but row square is always positive.
Yeah, so that means that I know exactly U0. U0 I know, okay? So congratulations, this is the first camera parameter that you have recovered exactly. Up to now, we recovered R3, but it was up to a sign, okay? We didn't know the sign of it, but U0 I know definitely. By the way, U0 cannot be negative anyway, so because it is just in the middle of the image. So we already know that, okay? Using the same trick, if I multiply A2 with A3, this is A2 with A3, so these two will cancel out, and if I multiply these two, I will get V0, but again, I have to divide this value. I have to multiply this value with row square, which is already known. I don't get affected from the sign of the row here, which is always positive. Okay, so U0 and V0 I know. Okay, let's put them back in. I know this one. I know this one. I know this. I know R3 and R3 up to a sign. I know these parts. Okay, what I don't know is the alpha, beta, theta values, and R1 and R2. I mean R1 and R2. I don't know those. Good. Okay, let's try to find them. So as you see, what we are doing is just linear algebra work. Okay, we are doing some mathematical calculations, linear algebra calculations. We take advantage of the orthogonality of the rotation matrix R so far, right? We said that the rotation matrix R is orthogonal, and that's why we said that RT times R or RRT is identity. That's what we said. That's how we recovered this one. up to a sign. Okay, and we are going to do this similar stuff. What we did was I take the dot product of between these two. How about if I take the cross product of these two? What would happen? If I take the cross product of these two, let's think about it. If I take the cross product of these two lines, this 3-element vector and this 3-element vector, what would it produce? What is the cross product of A with itself? What is this? If I take the cross product of A by itself, what would I get?
A vector that is perpendicular to this A space.
But I mean, what you are saying is correct for this one. If A and B are different, a vector that is perpendicular to both of them. But these are the same thing. So there are infinitely many perpendicular vectors to the same vector. So what is the solution for what is the result for this one? It is 0, right? It is 0. So if I do the cross product between this row and this row, you would get this times this is 0, right? So this would cancel out. How about this one? If I multiply R3 with R2, what would I get? These are scalars, right? I found them. What would I get if I cross product R3 with R2? R3, R2. Do I repeat what you said before? You would get
R3 and R2 are perpendicular to each other because they are axis of R.
yeah, and the cross
and the other one beta over sinus theta is a scalar.
No, it's not a scalar. No, if you cross product two vectors, you would get another vector.
Yeah. Oh, you will find R1.
Yeah, exactly. It's going to be R1. So depending on the order, sometimes it is minus R1, sometimes it is R1. I mean, if you switch spaces, okay. R3, R2 is minus R1. R2, R3 is R1, okay? So it's a right-hand system. So if I do that multiplication cross product between this row and this row, what you're going to get is R1 times beta over sine theta. And this will cancel out. So I am getting something. If I do the same thing here, between this one and that one, between these two I would get 0. Between here I would get R1, and between here I would get R2. So we are getting something for the R2 and R3, right? R2 and R1, sorry. R2 and R1. So that's what I'm going to do next. But it looks like again I am out of time. Let's take 10 minutes of break. After the break we will continue, and let's try to find the rest of the parameters. Okay, let's be here around 15:37.
İyi akşamlar hocam.
Güle güle hocam, yine gel. Okay, so we are doing the operation that I mentioned a few minutes ago. Instead of doing the dot product between the rows of that matrix A, now we are doing the cross product between them. So A1 and A3. Okay, remember we have always this row square, but we know the value of the absolute value of the row square is no problem. If I multiply these two, I would get minus alpha times R2. Okay, here. So R3, R1 is minus R2. R3, R3, R2 is R1, not minus R1, but R1. So I get this one. And R3, R3 is 0. And I would get, if I do the cross product between these, I would get this one. So it looks like, I get nice stuff from this one. By doing the cross product, I get the U0, V0 without any ambiguity. But here I didn't get these. I get the R1 multiplied with this some numbers and these two stuff. So at least I'm getting something about R1 and R2. But if I take the length of this vector, this is a vector, right? If I take the length of this vector, so R1 times R1 is 1, okay, I know that one, the length. So I multiply these two and take the square root of it, I would get this one. So if I cross product A2 with A3 and take the length of the resultant vector, I would get this one. Absolute value of beta over sine theta. And again, if I do the same thing, I would get, how could this happen? How could this happen? Because I am getting the length of it. There are taking the square of it. If I take the square of this vector, R2 squares will be 1, R1 squares will be 1, and these two multiplied together will cancel each other. So it's going to be alpha square minus cotangent square theta, and that's going to be sine theta. Okay, so I know many things now about sine theta, alpha and beta. Okay, so there is another trick here. If I multiply this one with this one, dot product, and if I divide them, these two, okay, I would get cosine theta. If I multiply these two, these will cancel out, and this one is going to give me the this one will cancel out, and this one is going to give me 1. So minus alpha times beta over sine theta times cotangent. Okay, I get this one. And if I do this one, okay, this is the result. And if I divide them, let me try to see what I am getting here. So I am going to do the dot product between these two. So these will cancel out, and this one will be R1s will cancel out. So it's going to be minus theta times cotangent theta times beta here over sine theta. Okay, and I'm going to divide this by these two, alpha sine theta times beta sine theta. Okay, and in that case, if I do that, I would get the cosine theta. Why? Because I have the cotangent over sine. If I do the math, you will get the cosine theta. So I know the theta now, without any ambiguity. Without any ambiguity. And alpha and beta are, how is this? Rho square, I know rho square, exactly. Okay. Yeah. If I know the cosine theta, I know the sine theta. Okay. If I multiply this value with sine theta, another rho theta, I would get alpha. Okay, good. And similarly, I would get the beta. So I will get both alpha, beta, and cosine theta. Exactly, without any ambiguities. Without any ambiguities. So far, what do I know? I know u0, v0 without any ambiguities. I know cosine theta. I know alpha and beta. Okay. For the intrinsic parameters, it looks like I know everything. Okay. For the intrinsic parameters, it looks like I know everything. For the extrinsic parameters, I know R3 up to a sine. So I need to get R1, R2. Also, I need to get the translation vector. Okay. So these are the things that I know. It looks like I can get R1 by doing this. Okay, A2, A3. A2, A3 is this one. Oh, okay. I know beta and sine. Now I can get I know this one, right? I know beta and sine, so I can get R1. Exactly. Without any sign ambiguity. If I know R1 and if I know R3, then if I cross product them, I would get R2. That's what I am doing. Okay. I know R1, and if I know R3 and if I know R1, I would get R3, R2. So I know all of them. But there is an ambiguity with R3 because there is a sign problem with there. Okay. So I need to deal with it. Okay. So how about t values? Where do I get the t value? Oh, okay. I know the t values. Why? Because t value is the, let's go back to the definition of the m. Where is my m? Okay. This value of m is tz. I know the rho value. I know the rho, but the absolute value of rho. So I know tz. That's fine. I have already recovered beta and alpha and u0. Okay. So I know tz up to a sine. I would put it in here. I would put it in there. And I can get ty up to a sine. And similarly, I do all of that stuff. I would get tz, tx up to a sine. So I can produce tz, tx, and ty up to a sine. So I need to find the sine of that row. How would I find the sine of that row? It is actually not that difficult. I could have done this at the beginning. I could have done that at the beginning because the sine of the epsilon can be calculated using the sine of tz. Tz cannot be a negative value because remember our coordinate system? We say that if this is my camera coordinate system, okay, if this is my image plane like that, all the points in the real world has to be in front of the camera. So their depth values has to be positive. So the value that I recovered for tz, if it is negative, then I have to put epsilon as negative. If it is positive, then epsilon is positive. And that's it. That's going to be it. So the sine for epsilon can be calculated using the sine of tz. So I recovered everything. I recovered all the rotation matrices, all the tx, ty, tz, and all the parameters inside this K. But that doesn't mean that the values that I found are perfect. because I did not remember. I recovered the rotation matrix, but I don't know if that rotation matrix is orthogonal. So what do? I take the single value decomposition of the recovered matrix, and then whatever the diagonal values are, I replace it with an identity matrix and multiply them, back project them together, and I would get the value of R. Okay, that's it. So we recovered R, we recovered T, I recovered alpha, beta, theta, U0 and V0. So it sounds complicated a little bit, but it is not actually. All I did was I recovered M first, the projection matrix. Then we said that the projection matrix is not a unique projection matrix. It is up to a scale, and using the orthogonality of the rotation matrix, I played lots of tricks of orthogonality, multiplied those m columns with itself, using the rules of the cross products and the dot products. I recovered all of these parameters one by one. Okay. Remember what I said at the beginning? I said that OpenCV doesn't do the camera calibration this way. This method of doing the calibration, I can tell you how it is done in 1 or 2 hours. Okay, like I did today, 1 or 2 hours, because I can tell you all the things that I never tell you anything. I never told you anything that you didn't know or you are supposed to know. Single value decomposition or cross product or dot product or the orthogonality. You already know that, or those are very simple stuff to learn. Okay, so I can teach you those, but this way of calibrating stuff is not easy to do in the regular world, because I need this calibration object. Okay, this is a three-dimensional object. It has to be specially prepared. The planes, this XY plane, XZ plane, YZ plane, okay, they all have to be prepared, and they all have to be perfectly perpendicular to each other. Okay, so those are some very difficult criteria to achieve. So we don't like this kind of method much. Instead, OpenCV gives you another method. This method is doing this. You print a calibration pattern like that. Okay, you print it on a regular paper like that. Okay, you show this pattern to your camera. Okay, you take an image of it. When you show this pattern to your camera, you take an image of it. Okay, this point here, the point, let me use blue. The point here, this one, looks like this is your coordinate system 0, 0, 0. It becomes your 0, 0, 0. Okay, and this is here 1, 1, 0. Okay, this is here 2, 1, 0, etc. It becomes like that. So in the z direction, let me do the z direction more correctly. Z direction is this way, up, right? In the z direction, I don't provide anything, but I don't provide a single image. I provide many images, like the second image is this one, and the third image, and the fourth image. The important thing is that you don't change your camera position. Your camera position is always the same. You don't move it. Okay, and then you capture many images of it. From the images, you determine your corner points using the corner detection algorithm, or there are very nice corner detection algorithms on OpenCV. After doing that, you provide all these points, okay, to the Calibrate Camera function. So input array of arrays, object points, Okay, input array of arrays image points, object points, and the image points. Object points are your XYZ points, and the image points, and the size of the image, how many images you provide, etc. And as a result, this function gives you your camera metrics as the intrinsic parameters, okay, your R vector and your translation vector. On top of it, it gives you your distortion coefficients. Remember, our lenses are not perfect, okay? So we assume that there is a radial distortion happening, and this method is robust enough to recover the lens distortion parameters for our system. So lens distortion parameters are other intrinsic camera parameters. So it is much more practical. Why is it practical? You don't have to buy a special three-dimensional calibration pattern. The calibration pattern is printed using this, using a simple laser printer and a piece of paper, and you put that piece of paper on a planar object like a bookcase, and that's it. That's it. You find those chessboard corners, and you provide them to your Calibrate Camera routine, and it works very nice, very robust. And the more points that you provide, the better your algorithm will work. And on top of it, it gives you the distortion coefficients too. Okay, so I guess that's it for camera calibration. You might say that if you are going to use this technique, why did you show us all that mathematical details of getting the parameters out of it? Well, this technique seems simple, but the mathematics underneath is more complicated than the other one. I mean, it seems complicated, but actually it is not. I mean, it doesn't require you to know many things about linear algebra. Only things that we have used so far is single variable decomposition. It's a first year or second year course thing, right? And cross product of two vectors, dot product of two vectors, and the orthogonality. That's it. I didn't use anything other than those. Okay, so it is involved a little bit because it is using trick after trick after trick. But I mean, this is usually life. Once you get used to this kind of stuff, you will realize that we keep doing the same thing over and over again. Actually, we did that. I mean, we used the orthogonality of the matrix R in many places. Okay, any questions about the camera calibration?
For our this way to solve calibration parameters, we have a UV point. We work on P in camera coordinate. Here it says chessboard code find pixel values of UV for each different layers. I didn't understand what OpenCV finds in this case. Only UV coordinates and then solve.
OpenCV, when it runs the chessboard corners, OpenCV finds the UV coordinates in the image coordinate system for this image. And if you have more than one image, and you should, it doesn't work with a single image. You should have many images with different points of view. So you show your pattern at different angles, okay, at different positions on your screen, and for each one it finds UV points. Okay, it finds UV points, and that's why you provide input array of arrays. Okay, so for each what do I say? For each image you have an array of points, but you have many images, so you have an array of arrays. And then OpenCV assumes that the first image that you showed it has a corner point 0, 0, 0. That's your real world 0, 0, 0. And your x is that way, y is that way, and z is perpendicular to both of them. And with that assumption, it gives you the intrinsic and extrinsic parameters. Okay? And there are related functions in OpenCV. I mean, this Calibrate Camera calibrates everything from the scratch. But if you have, let me try to find it. If you have the intrinsic parameters, you don't have to provide OpenCV camera calibration. Do I have any videos that I can show you? Yeah, okay, somebody provided this nice video. So these are for the distortion parameters, and these are the parameters of focal length, principal point. Okay, and once you are done this and that, okay, finds it. Let me show you this one. You don't hear the sound, right? You don't hear the sound of the music, right? No, you don't. Okay, that's good. Okay, so every time you take a picture, all the corners are calculated, and this guy is showing this plate at different angles. Usually you take 10, 15, 20 images, and you try to put this plate at every position, many positions in the image, so that I can get the distortion parameters, right? Okay, so this guy obtained it. So these are the parameters. Okay, these are the image points again. Back projection stuff. Let me see if this guy is doing anything about back projection. No, it doesn't. He doesn't do it. So basically, they explain how the parameters work, how the general procedure work. But I'm going to find some calibration functions. Not good. Okay, I'm not going to look at the tutorial. Let me go to the documentation itself. Where did it go? Okay, all I don't want the images. Okay. Is this a tutorial again? I don't want this. Okay, corners. Find the chessboard corners. Corner subpixels. you find all the corners, then you call Calibrate Camera. Let's go to that one. Okay. So these are different methods for doing the calibration, and I am trying to find the Calibrate Camera. This is the most object points, image size. This is the one that I showed you. Intrinsic parameters. This one, image points, image size. See, this one takes the camera matrix as input and distortion coefficients as input, and it only produces translation vector and rotation vector. So that means that I already know the intrinsic parameters. All I need is the extrinsic parameters from you. So most of the time we could use this to find where the camera is in the real world. Okay, to find where the camera is in the real world. Can I see this? What is this RO? No. Okay, I'm going to click this one, Calibrate Camera. This is not provided for convenience. It differs from the above function only what argument it accepts. Do I have an example for this one? Since for the extrinsic parameters, since the degree of freedom is just 6, I don't need many points. Also, by looking at a single image, I can get my rotation matrix plus the translation vector, and by looking at a single pattern, chessboard pattern, I can recover my extrinsic parameters very easily. If I can recover my extrinsic parameters, that means that I know where my camera is in the real world. Okay, I know everything. I know where my camera is in the real world. I can do many stuff, because if I know where the camera is, I can do all kinds of projections between the real world and the image space. Okay, that's something that we can say. Okay, good. Are there any questions? So if there are no questions, then this is one thing that you can do. Okay, let's say I have this is the image, this is the calibration pattern that I showed to my camera. Okay, I know my intrinsic parameters. Okay, I know this K. I don't know R and T. I don't know these two. Okay, to find R and T, only a single view is enough. Only a single view enough. From this view, I found this 1, 2, 3, 4. Okay, 4 correspondences. I get those. 4 correspondences. I get those, and there are 3 in here. Okay, 3 in here and 3 there. 6 unknowns. Since each one has x and y components, I have 8 equations. By looking at these 8 equations, I can get these R and T. Once I know R and T, I know M, right? Since I know M, I can say that M times 0, 0, 0, 0. Okay. Where is the sorry, not 0, 0, 0, 0, 0, 0, 1. Okay. Where is my origin of my image? So this will tell me the origin of my image, and I can mark it on my image. So, and then after that, I will say, where is M times 1, 0, 0, 1, and it would give me that one too. So by looking by giving these kind of standard position, I can draw a cube on my image like that, a three-dimensional cube, on my image. Oops, okay, do this that way. A three-dimensional cube on my image like that. And whenever I change this pattern, okay, my cube changes accordingly. Okay, so I am doing some kind of an augmented reality work, if you know your intrinsic parameters. Okay, so that's good. Any questions?
If you know intrinsic and extrinsic parameters of an image, by some algorithmic manipulations, we can change the coordinate system of image with what in, I think it's like augmented reality.
Yeah.
Is augmented reality produced by this way?
Exactly. With the augmented reality applications, your camera is calibrated because it works on your cell phone, and cell phone is calibrated. You already know the parameters for your cell phone. Okay? And since you know your intrinsic parameters, for the extrinsic you assume some kind of a real world coordinate system by looking at a pattern like that. Okay? A pattern that you know already. And when you give those coordinates to the camera calibration, that returns you the RNT parameters. Now you know where your 3D points are on your image, so you can draw anything you want on your image and three-dimensional objects. When your pattern changes on the image, you change your RNT accordingly. That's how they do the augmented reality. And with the augmented reality, the important thing is that how precise you can find these points on the images. So if you that's called the tracking. Okay, if you do the tracking right, so your augmented reality will work very fine. If you don't do the tracking right, your augmented reality system will not work very well. Okay. Okay, good. Then if there are no questions, then I will start talking about the next chapter which is about motion. Okay, so far we did not talk about motion at all. Everything was static. We take a single image of a scene, we do the edge detection, we did the feature point detection, key point detection, etc. Later we looked at the same scene from two different angles, and we tried to establish the fundamental matrix, and then we talked about the calibration, but every time the scene was static. Now we are going to talk about motion. What if our camera is moving? What if the objects in our scene are moving, etc.? Can we produce more real-world related information about this motion? Okay, and the answer turns out to be yes. You could do a lot more if you are doing the motion analysis on your images. Okay, there are many applications of motion from video. Okay, one thing is structure from motion. Remember, we can get the depth from the stereo, right, by doing the triangulation. We could use similar ideas to get the depth or structure from the motion of the camera or from the motion of the objects. This is called structure from motion. Okay. Some people does motion recognition. Okay. Recognition by motion. And in fact, we do this a lot as human beings. As human beings, we use motion to recognize stuff. There is a simple experiment. People have been doing this experiment for a long time. Let me try to find it. I'm going to show you a few frames. If I can find them, I think I put them in here. Yeah, I think I found it. This is the one. If you have seen this before, just don't talk, but I did not show it yet. If I show you, if I show you this, there's dots. What do you see? So it looks like there is a group of dots here. There is a group of dots there, and there is a group of dots there, but you cannot make anything out of them. You cannot make anything sensible out of these dots. But if I start moving these dots, okay, if I start moving these dots around, you will notice something. You see it, right? What was the moment? The one that I showed you a few minutes ago? Look at this one. What does this guy do? How about this one? What does this guy do? That guy is sitting on a chair or something, right? And by the way, when I say guy, nobody has objected. Is that a guy? Yeah. Somebody is doing these movements. Let's look at them one by one. This one is walking towards me, right? And this one is jumping from a crouching position. This one is climbing a stairs and climbing back. This one is sitting on a chair, high chair. And this one is doing what? Applauding or something? I don't know. And on top of that, and I think this is a male, right? Not female. It's a male person. This is how males work. This is how males walk. It looks like. Yeah, most probably. Is this a child or grown-out person or old person? I think this is a person in 20s or 30s. This doesn't look like a child. Is that correct? This is not an old person. Yeah, this is definitely a male. So how can I say this kind of stuff? By looking at a single image, I cannot say any of these, but by looking at the motion, I can do lots of recognition. So humans are doing that kind of stuff. So why can't we do the similar stuff with the computers, with the computer vision? So all I need to do is process more frames, one after the other, and try to find relationships between them. That would be our way of processing images for the recognition only. So That doesn't mean that we are going to use motion for recognition only. We are going to do structure from motion, the depth estimation from the motion, okay, recognition from the motion maybe, or using the motion information, we can do lots of video compression, okay, we can do surveillance, who is doing what, or human-computer interaction. Can I communicate with my computer using my hand gestures, etc. So motion has lots of interesting stuff to work on, and many researchers are interested in analysis of the videos of the human motion or the object motion, etc. If you look at this, let me try to do this continuous mode. Okay, good. No, I don't want to do that. Can I do this in the other viewers? I need to sudden. Okay, maybe F11, control F11. How do I get to the full screen? I think Shift F11, Control F11. Do you guys know how to go to full screen in Edge?
F11.
Just F11? Yeah, just F11. And so how do I go to just single page? Single page like that. Okay, good. So it works. So if I show you these two images, do you see any difference between them? The answer is no. Say no. Say no. Okay, good.
No.
Okay, good. But if I show you this image and this image right after each other, what do you see?
Something is going upside.
Yeah, something is moving, right? So these two images are different, but if I show them one next to each other, you don't see the difference, but if I show them one after other, due to our motion sensitive cells in our eyes and brains, I can see that there is something moving. So there are lots of cells in our eyes, in our biological systems, that are sensitive to motion. So this is stereo stuff, left and right. Maybe you can find it, the difference if I show them to your left and right eyes one by one. But if I do this, okay, one after the other, definitely I can see the movements. So the motion carries lots of information for humans, and we should be able to take advantage of it for the computer. So that's what I'm trying to say. Okay, so that's the random dot example. Okay, good. So in this analysis of the motion, that's what we are going to assume. We are going to assume that we have many images, n images or frames acquired at different time instants. Okay, there is a delta t time difference between the images taken, and we usually label our images with t0, t1, t2, etc. It goes that way. Okay, and usually these two assumptions, okay, makes our life a lot easier. Sometimes we have to stop assuming these, but most of the time we do that. Okay, every time I take the picture of a scene, the elimination conditions do not change. That's one assumption. The second assumption is, okay, the image changes between frames are caused by the camera or scene motion. Either I'm moving the camera left, right, up, down, whatever, or the objects in the scene are changing. Okay, we don't assume that the lighting is changing or that kind of stuff, or I am changing the camera parameters. I am not changing the camera parameters. If I change the camera parameters, our images are different too, but I am not changing them. I mean intrinsic parameters. So those are the assumptions. It looks like I am out of time. I wanted to give you a simple example of how the motion could be very useful for calculating stuff, but it looks like I'm going to do this next week. Okay, that's it for today's work. Okay, I'll see you next week.
Thank you.
Bye.
The first lesson we talked about single decomposition. So if we have some questions, can we bring a legal part of next lesson for questions about?
Sure, yeah. And anytime if you have a question, beginning of the lectures, end of lectures, I can answer them, no problem. Okay. Okay, see you next week.